Just
from our announcement.
yes. This one looks original. No wonder.
Control.
You only deal with two interfaces.
Because I wanted to start. Okay, good morning, class. Good morning to you all. Good morning, and you are welcome to Section 101 again. And like I told you yesterday, today is going to be my last class with you on thermochemistry. And I already informed you to prepare to ask your questions so that we can take time to attend to them. So it gives me great joy to be here with you again this morning. And I hope you are ready. And we also understand that many students are writing MTH 101 test this morning. But as many people that can be online, we encourage them to be online. However, the notes will always be there for students to check again and catch up with whatever they would have missed. So we are going to start the lecture now. I'll just continue from where I believe that you all tried to be considered for Haber cycle, bond energies, and bond dissociation energy. So we will just continue from there. I think as at the last class, you had the opportunity of seeing this slide that I'm displaying, where we have some of the constants for the bond energies. And I told you, because many of you were asking me if you have to determine the bond energies for every question, and I told you that we will give you those ones as constant values. However, if the question requires that you should determine it, then you will have to determine it. But it is not as if we expect you to cram the bond energies in any situation. If you are calculating anything, it's just a test of your knowledge. And I'm sure you will understand it from where I stopped. So for us to continue, you will remember that I took you through this question. Just a minute. So, I've been checking.
It's not your.
So back to this question, which was the last one I solved for you yesterday. And I said you should calculate the bond energy. So that's a question that requires that you should calculate the bond energy of a molecule. But I told you that generally these are given as constants. And going over this question, the question says calculate the bond energy in the hydrogen chloride molecule from the following information. So if you look at the information, we even have the bond energies of chlorine given, and then hydrogen, where you have H. I explained this. So the bond energy given is for H bonded to H, because that is what gives you the H2. So for HCl, you also have the bond energy given as, okay, the bond energy of HCl is what you have to calculate. Then for Cl2, this is the unknown. And then for Cl2, you have Cl bond. The bond energy has been given as 238 kilojoule per mole. And I think that already answers the question on the minds of many of you, because this is how you have calculations that may demand that you calculate the bond energy. But generally speaking, These are constants. These are established values, and you don't need to cram them. So I showed you the solution that you can use bond energy to work out delta H of formation, the standard enthalpy of formation values for hydrogen atoms and Cl atoms. So you see, this is how we worked that out yesterday. And then for Cl, we worked it out because we already know the amount of energy that is in this bond. That is what we refer to as bond energy. And if you have Cl to Cl, and in the reaction, you have also been given how you have the number of moles to correlate. So we solved this problem yesterday, but I just used that to explain that the question many of you asked yesterday will not be a problem. Also, I gave you this question, which we solved, where I said you should calculate the bond energy of carbon-carbon bond, single bond, in C3H8. You will recall that I gave you the structure of C3H8 to allow you see the configuration and determine the number of bonds. So for all these ones, what you have, I explained to you, these are CH bonds, and you can see there are 8 of them in the molecule. So I advise you not to just examine it physically by physical inspection, but try and draw out the structure. So you have 8 of CH, and then for CC single bond, you have 2. So that is how you have 2 CH bonds that we used to do the calculation. So the question that somebody asked me yesterday about the possibility of double bond requiring that you should divide by 2 does not arise. The C double bond rho here, for example, has a constant bond energy. If you have CC bond in ethylene or alkenes generally, this also has a constant value. So it is not the double bond energy it's not the double bond information that is given that you will divide to get the C single bond C. No, they are of different values. I'm sure you know that the amount of energy in double bond will not be the same as the energy in a single bond, and of course it's also not half of it. So don't assume that because you are looking for CC bond, you have to divide the value for C double bond C by 2. So these are a few things I feel that I should point out to you before I continue. We solved this problem yesterday, and I want to believe that it is clear to all of you. Also, some of you asked me a question that do you reverse the bond energy values for reactants and products in all cases? Let me remind you, I gave you this equation at the beginning of this topic, bond energy and bond dissociation energy. So I explained again, and I'm taking time to explain it now, that when you are using delta H of reaction based on delta F, that is the enthalpy of formation of maybe the reactants and the products. So you have for all the reactants and all the products. When you have to deal with delta H of reaction in such a situation, you will have to bear in mind that it's going to be the summation of all the enthalpy of formation for the products. Minus that of reactants. That is how it goes. But when you are dealing with bond energies, you will have to take away the summation of the bond energies of all the products from the summation of the bond energies of all the reactants. And I explained this to you earlier on, that when you are breaking a bond, energy is absorbed because you have to put energy. So that changes the sign. And that is why this equation is having this reversed approach. So it is not, don't mix them up. If you take your time to read, you will definitely understand what we are doing now. The slides are very clear. The examples are the examples are very straightforward. So I believe you can continue from there, having clarified some of your issues. It's just giving me all this. Just hold on for us while we are doing some of these. When we are attending to technical issues, I want to give you the code for today. The first code, the first attendance code. Please get ready to write the code. It has all upper cases for the letters, but it starts with 7. 7 RAPS. 7, that's figure 7. R for reaction, A for acid, P for product, S for solution. 7 RAPS. That's the attendance code, the first attendance code for this morning. 7 RAPS. Okay, so you are welcome back to the class, and we will just continue from where we stopped. I'm sure I've made a lot of clarifications on the questions that were asked. So let's take another example. This question says, determine the bond energy of CO2 and hence the average bond energy of C double bond O in CO2, given the following information. So in this case, we have three equations given. So this is one, this is one, this is two, and this is three. In the first reaction, we have carbon in form of graphite becoming carbon atom in gaseous state, and the delta H for that process is given as 715 kilojoule. If you look at what you have, graphite as solid and carbon as gas, that tells you that the delta H there is delta H of sublimation. So the change in enthalpy in standard states, in standard condition there, is for sublimation. And if you look at the second question, it says oxygen gas giving you oxygen atom in gaseous states. So what you have is atomization, because from O2, you are breaking that bond to give you the atoms. So you have two oxygen atoms would have been formed, but for us to call it enthalpy of atomization, I told you that you must be forming 1 mole of the product, and that is why we have it written as half. So the equation has been balanced for you. The third one says carbon in solid form as graphite reacting with oxygen to give you CO2. Definitely what we have there is 1 mole of CO2. This is actually testing a lot of principles that I already taught you about enthalpies of reactions, and then we will see the bond energy determination later. So if you look at this, what you have is the standard enthalpy of formation for CO2. So how do we solve the problem? The question again says determine the bond energy of CO2 and hence the average bond energy of CO in C double bond O. So if you look at this reaction, what you have in the first step, I told you is sublimation, in the second step is atomization, and the last one is the enthalpy of formation. To solve this problem, some principles are also tested. So if you look at equation 3 is actually given as the enthalpy of formation, but if we reverse that, you have the atomization take place. So you are going to form the atoms from CO2. In fact, I'm not reversing that. Sorry, I'm not reversing that. What I'm actually doing is to see how we form CO2. So how we form CO2 is from carbon and oxygen. For atomization of CO2, it means taking the bond in CO2 to give you carbon and oxygen. And if you balance that equation, you are going to have 2 of these. I shouldn't write it there. So you have 2 of oxygen. So if that is the case, then we need to look at all the equations that we have earlier on and see where we get the values that we need to be able to determine the enthalpy of atomization first. The enthalpy of atomization of this first, because it's going to lead us to determining the bond energy. If you don't have all the atoms giving you CO2, then you cannot know the bond energy of C double bond O in CO2. Don't forget, CO2 is going to have C double bond O, 2 of them. So you have 2 CO there, but we are still going there. That's not where I want to start from. So if you come here, the enthalpy of atomization can be determined. Since you know the enthalpy of atomization for oxygen and then you know the enthalpy of formation of CO2. That's the point. You know that of CO2. So if you look at this reaction, we are writing it in form of atomization, and we are going to use the enthalpies of formation. So it then means that we will apply the expression for delta H equals summation of N delta H of the products minus summation of M delta H of all the reactants. So the product comes first. And the product in this case, you can identify it from the equation. So you have graphite, carbon as graphite, you have two oxygen atoms as the products. And for the reactants, you have CO2. So you have this equation as written here. So you look at all the equations. Actually, this requires you to reason and reason before you can start to attempt the question. So if you look at all the terms and values that you have been given, we have the delta H of sublimation for graphite, and then we have the atomization value for, delta H of atomization for oxygen. Sorry that this one is, we cannot do the subscripts in that state, but I'm sure you understand. It's not 2O, it's O subscript 2. Or O, it's not O and 2 together. That's what I mean. So if we substitute all the values, we have delta H of sublimation, and we have 2 of oxygen formed. So we have to multiply this by 2, and that is what we have there. You multiply this by 2, and then you have the expression for the formation of CO2, because we have now turned the reaction around. So this is now the reactant, and the equation is as presented there. So if you substitute all the values, you will get delta H of atomization of CO2 to be equal to 1606 kilojoule per mole. I wish time will permit us to say that you should substitute those values yourself, but I don't think we'll be able to do that. Now, yesterday I explained to you that when you look at any bond, we are talking about delta H and relating it with bond energy. I gave you an example earlier on how you reverse it. So you can see clearly that here we are not talking about bond energy. We are talking about the enthalpy of formation for a molecule, and then you obtain the delta H of atomization. For that singular molecule, you can as well relate it to the bond energy of the molecule. So the bond energy then talks about the total amount of energy, the atomization value that we got is referring to the energy that is required to break all these bonds down to give you all the atoms in CO2, all the atoms separated by infinite distance. So that is what you have. And that is why it is easy to relate the delta H of atomization to bond energy in this case. And I put it in red so that you can pay attention. Now, the structure of CO2 is given here, which means that there are 2 C double bond holes there, as explained earlier, and that is what I'm also showing you here. So it then means that the average bond energy of CO in CO2 will be this value that we have obtained for the bond energy of C double bond O and C double bond O divided by 2, because you can readily divide this by 2. You have the same type of bond in this molecule. So 2 types, one type of bond. Remember yesterday I told you, you have to be sure of the type of bond and then know the number of bonds, of such bonds. So each type, we have its number. So you have 2 here, and that is when you can divide by 2. So what you get is the average bond energy of C double bond O in CO2. And the value is given here as 803 kilojoule per mole. I will give the second attendance code now, while you can pause because I have a little time to take your questions. You can pause and ask your questions immediately after. So I'll give the second attendance code now. The second attendance code for this morning is C93X4. C for carbon, 9, 3, X for xylophone, 4. Don't forget the letters are in upper cases. C93X4. So maybe before I take another example, I would just like to know what to think about all that I've been saying. I want to see if you have questions so that we can take the questions before I finish the remaining slides. I would like to take your questions, especially on the topics we've been considering under the main thermochemistry consideration. So feel free to ask your question. And if you don't have any questions, then I will shift the time for questions to the very end of the class. It's a glitch. They're not. They've not been responding. So you are welcome back to class. Thank you all for being here. I want to ask if you got the code, the second code that I shared. Oh, somebody is asking for the first code. You probably joined late. I want to confirm if you got the first code, the first attendance code for this morning. And like I told you, that I would just like to take your comments and questions. Let me know if you are hearing me. Let me know if you got the second code. Comments, questions. Let me know if you are hearing me. Let me know if you got the second code. Oh, good. You are hearing me. I'm happy to know that. And did you receive the second code? The second attendance code? Thank you. We are with you, ma. Thank you, Ajadi. Please confirm if you received the second attendance code. Oh, yes, we did. Thank you. So we are good. And very soon we will just conclude this topic. Thermochemistry has been very interesting being with you. So the problem that I solved earlier on for the bond energy of CO2, from which we obtain the average bond energy of C double bond O, I have used the Hess's law of summation to approach it. And I think I found it simpler anyway. So you can just follow me. This may be the best thing to do. So if you look at it again, here we have this first one. We have the first reaction, we have the second, and then we have the third reaction. So if you look at these as steps, step 1, step 2, step 3, then to determine the bond energy of CO, which is also the same, CO2 rather, the bond energy of CO2, which is also the same thing as delta H of atomization of CO2. Actually, this should have a superscript. Standard enthalpy of atomization of CO2. We rearrange the equations to ensure that CO2 appears on the left-hand side of the equation, and then we apply Hess's law. So let's go. If you look at the first step, second step, and third step, apparently CO2 here is on the product side. So we can reverse that equation to obtain a positive value of delta H. So once we reverse it, we have made CO2 to be on the reactant side so that it suits the equation that we are considering. Let's go back to the equation that we are considering. The equation we are considering, which I wrote earlier on, is this. So for CO2 atomization, you will find this approach very useful for this question. So if you look at all of this, we can cancel the reactants or products that appear on both sides. So we can see oxygen gas, we cancel out oxygen gas in reaction 3. So if you look at reaction 2 and 3, we can cancel out oxygen and cancel out oxygen. So if we do that, what are we left with? We still have carbon on this side, and then we have CO here. So what then do we have? When we sum the 3 equations, we will be left with CO2 gas, then we have carbon as graphite, and then we have 2O as expressed here. So the carbon as graphite actually cancels out. carbon as graphite cancels out in step 1 and step 3. So going over it again, step 1 compared to step 2, they don't have similar reactants or products. But if you go to step 2 and 3, you cancel out oxygen in both steps. Then if you look at 1 and 3, you cancel out carbon as graphite. And so the overall equation becomes what we have been looking for, which is the delta H of atomization of CO2. So once you atomize CO2, you know that you are breaking it into its elemental composition. If you break this and break this, then you will have carbon and you will have 2 oxygen. That's what we mean. So what then is the delta H for this process? That is delta H of atomization. And so you obtain delta H of atomization of CO2 as 1606 kilojoule per mole. And the average bond energy in CO, because there is only one type of bond, which is C double bond O. And there are 2 of such type. So that gives us the confidence to say all we need to do is to divide that by 2. And once you divide it by 2, you obtain 803 kilojoule per mole, which is the same as what we obtained here. So what we did here, you can as well do it another way by applying the Hess's law. In this case, we're looking for delta H of atomization, considering all the reactants and the products that are involved from all of the 3 steps that we have been given. But in that case, we just looked at what we need to reverse and then what we need to cancel out. So let me take us to the next slide, which actually has more examples to practice. But like I said earlier on, I would like to take your questions. Let me pause and take your questions. The network didn't allow me the other time. So let me have your questions, because what I have left is actually more examples for you to practice. Yes. If you have any question, feel free to ask me now. We have the next 10 minutes to attend to questions. Any question on thermochemistry at all, from the beginning when we talked about intermolecular forces to the point where we talked about entropy, and then we talked about free energy and enthalpies of reactions, to Hess's law of summation of enthalpy. You are free to ask me any question. And then to Born-Haber cycle, bond energies, and whatever you want to ask. I'll gladly take your question. I'll be waiting to receive them. So while I'm waiting to see your question, let me be taking this example. I've put these examples for you to see that there are different questions you can come across in considering bond energy, bond dissociation energy. So if you look at what we have here, the question is about SF bond. So I hope you can see it very clearly, although I copied and pasted it from somewhere. It says the standard enthalpies of formation of sulfur in gaseous states, fluorine, SF4 and SF6 are as given here, respectively. The first part of the question says, use this data to estimate the energy of an SF bond. Use this data to estimate the energy of an SF bond. So you have SF bond in SF4. You also have SF bond in SF6. That you must know. Then you have been given sulfur and fluorine atoms in their gaseous states. So if you are going to form SF4, then it means you're going to have S having 4 fluorine atoms around it. So you will need S in gaseous state, sulfur, and then 4 of fluorine in gaseous state to be able to form that. And so we can determine the enthalpy of the reaction using the enthalpy of formation. And since we are using the enthalpy of formation to determine the enthalpy of reaction, then you have to bear in mind that the product comes first. If you look at the equation, it's balanced, and the number of moles of each of those atoms or molecule will be considered in the final expression. So you have delta F of SF4 as the product minus the summation of that of the reactants. So these are the reactants, and so you have 1S, and then you have 4 fluorine atoms. So if you come here, you will look at the delta H of formation for them, which you have been given as enthalpies of formation for all of these 4. So you need to be sure you carefully select the one that represents the term you are looking for. So for SF4, this is the value, and so we substitute it here. For S, you have been given 278.8, and then for fluorine, let's see where fluorine is. Fluorine is on the reactant side, so here you have that of fluorine as well, which is 79.0. So when you substitute all of this term, 4 of fluorine, that is why we have 4 in front of that value to multiply it. So if you multiply it by a factor of 4, you get that. So for our product, this is where the product ends, and these are the reactants. So if you substitute that, we get minus 1370 kilojoule. You can confirm the values. But that is not all. You are actually going to determine SF bond. So for the second one, you see formation of SF6. This is how you have it. And so in each of them, you can see that the delta S, the delta H of formation is determined. And once you determine the delta H of formation, then we will need, there's something that I didn't put, that was not put in that equation. So you have for SF6, it means you have 6 SF bond. That is where the solution lies. Unfortunately, I can't even find it in the solution that's provided here. So what you need to consider is to take the value for delta H of the reaction, which is minus this, and then you divide it by 6 to get the value that you need. So that is how you obtain the energy of SF bond. And if we do that correctly, let me use my calculator and obtain the value to finish up that question. So we have 1962 divided by 6. So the value is going to be 327 kilojoule, minus 327 kilojoule. So if you look at what we have in SF4 and you treat it the same way, I expect that you will get the same value. Now, the second question says, what are the delta HF values for S and F? Sorry, why are the delta H standard for the formation of sulfur and fluorine not equal to 0, since sulfur and fluorine are elements? What I explained to you earlier on when we're considering enthalpies also come to bear here, because sulfur and fluorine in their gaseous state, they are not the standard state of these elements, so they will not have the value of 0. Some of you asked me the question why oxygen molecule we have delta H of formation of 0, and I explained to you that that is the standard state in which it occurs. So for these elements, you will naturally think that, oh, they are elements, but they are not in their standard state. So always bear in mind the standard states of any atom or molecule that you are considering. So the second example here says, estimate the enthalpy of reaction below using bond energies in the bond energy table. Let me go back and see if you have left me questions, because those questions are more important than the solved problem. Nobody is asking questions. What is going on? You asked me a lot of questions yesterday. Okay, maybe because I've taken a lot of time to slowly explain everything. All right. Somebody said, can I help us recap the topic briefly? That's not going to be easy. Which of the topics? Thermochemistry itself is a topic that has many subtopics. Maybe you can be more specific, please. Is there any part of the topic thermochemistry that you do not understand? Ask me questions around that, because asking me to recap the entire topic will not be possible within the limited time that we have. Please, Bamidele Tolulope, I'll be waiting to hear the specific aspect of the topic that you want me to recap for you. So, nobody is asking questions, but I believe you have many examples already in this notes that will guide you as you read them, as you practice, as you revise. Don't forget, you can always come back to the lecture notes. You will find it in the archive. Please don't ask for first and second. Okay, today's topic, Bamidele Tolulope, today's topic. I don't know, maybe you joined the class late. This is actually not a new topic because we started it yesterday. We started looking at bond energy and bond dissociation energy yesterday. Maybe what I'll just do is to see if I can still take you through. We were not able to follow up, maybe because we were preparing for some other tests or classes. So let's see. I think this second question will also serve as a revision of the topic. It says, estimate the enthalpy of the reaction below using bond energies in bond energy table. So I told you that these are values that are known, experimentally determined, well established, and you don't need to cram them. So you are referred to the table. But here, the values are already given. You don't have to start looking for the table. So what you have is HCN plus 2H2 giving you CH3NH2, all of them in gaseous states. And if you look at the reactants and the products, you can determine the type of bonds around them. That is the first thing. I told you, always check out for the type of bond, check out for the number of each type of bond. So for HCN, you have H triple bond N and H. When you draw it out, you will have less problem. For H2, you have H bond. And for CH3, so let's take them one by one. For HCN, there is one CH bond here, and there is one C triple bond here. So this is the bond we are referring to specifically. So that takes care of the first reactant. For hydrogen, that is simple for you to know. So let's look at CH3. CH3 means that you have this, and then you have nitrogen, and then you have N2. Well, however you draw it is not my problem now. If you look at what we have on the board, we can determine how many types of bond. We can see clearly we have CH bond. We also have CN bond. We have NH bond. So this NH bond, how many are they? There are two. I've already started them. How many CN bond? We have one. Then we have CH bond, these ones, and we have three. So once you identify the types of bond, you can readily solve the problem. Oh, even the structures are here. So if I have to delete my notes, you don't have any problem. So we come here and solve the problem. For the reaction, you remember, in this case, we are using the bond energies. So this is delta H of the reaction, and we have to write the expression to show that delta H is equals to summation of the bond energies. In this case, the reactants will come first. Reactants, let me just use R, then the summation of the bond energies of the products. So that is what we have done. Simple. So we come back and look at all the reactants. We have HCN and we have H2. And all the bonds present in all these reactants, they are what we have substituted their values from the table. The only thing that you will need to do, apart from knowing the values of this HH bond, HC bond, C triple bond, N bond, triple bond N, the only thing you need to bear in mind is the stoichiometry. Once you add the stoichiometry, you'll be home and dry. Multiply by that factor. So here we have 2 of H2 bond, 1 of CN, 1 of C triple bond N. Triple bond N. So that is what we have on the reactant side. And on the product side, yes, my time is over. Yes, I have to quickly give the last code. Sorry, I took my time. Let's take the last code. QV6GX. QV6GX. QV6GS. Q for Queen, V for Venom, 6, G for gold, X for xylophone. So I think I've solved all your problems. I've answered your questions, and you can play around with the remaining examples that I put in the notes. They are just examples from past questions from the departments. If you want to have physical contact with them, you can go and look at the past questions and solutions that we provide. Have a wonderful day. Thank you.
So they have the slides.
There are too many examples all through the notes.
They have the slides as well as
they can download it.
I mean, congratulate you, Prof, for the successful completion of your stream.
Thank you.
welcome
you.
Welcome you on board.
Yeah, it's quite interesting.
Thank you.
For me.